So remember what I told you before, that just because there's something on it doesn't mean it's an actual transformation. You always have to look at the original equation to see what was there before and what's changed, right? So this one here is actually 4 minus x cubed. So this graph already has a reflection in the x-axis, because it's not with the x, right? If it was with the x, it would be in brackets. It's not. So it's a reflection in the x, and it's been moved 4 up already. So any of that that exists is not new. So I'm not going to say those transformations because those already occurred. Okay? When it asks you to describe the transformations that occurred to this function, this is the original. This is what it looks like to begin with. Okay? We aren't going to state those transformations. They happened. That's what the graph looks like. Okay? So what's new on A? There's a 3 out front. Why is it out front and the rest in brackets? What kind of stretch is it? It's a vertical. It's not with the x, so it's a vertical. And why did they put it in brackets behind it? Because when you apply a vertical stretch, what do you have to remember to do? Apply to everything, including the vertical translation, right? So they didn't just, they made it nice. They didn't apply it. Now what they could have done is they could have done 12 minus 3x cubed. It would have been harder for you to spot the vertical stretch, but they absolutely could have done that, right? Because when you apply a vertical stretch to an already transformed graph, it has to apply to the vertical translation as well, because you're stretching that translation. So, describe the transformations, cert. So we have stretches. So we have what kind of stretch? Vertical stretch by a factor of 3, because the vertical doesn't flip, change, switch at all, right? Horizontal does, vertical stays the same, as long as you have it in y equals. Vertical stretch by factor of 3 about the Now, if I were to move a point, if I were to do mapping, it didn't ask me to do this, but I always do mapping so we get used to it. Why do we use mapping? To move what? Points on a graph or just a point, right? Always. So if you're moving a point or you're changing a graph, you use mapping. So my original equation is xy. What's it going to be now? Is there anything new with the x's? No. What about the y's? 3y. Stretches and reflections multiply. Translations add or subtract, right? Now some people will say, but there's a vertical translation 4 up. Was that already there? Yes. So I don't put it on my mapping. My mapping is how it changes. It didn't change in that way. That way was there before. Okay? B, what's changed? The 4 is the same. The minus sign is the same. The x became what? 2x, and the 3 is the same, right? So the only thing that changed was that 2x. If it's with the x, what kind of stretch is it? Horizontal. Okay. And what do we always do with the horizontal? Reciprocal. Reciprocal. I don't know what I just said. Reciprocal. Horizontal stretch by a factor of what? 1/2. About the anything else? Any reflections or translations? Nope. Because all the rest of that was there before, right? So we don't state anything that was there before. We only state what's changed. So my mapping, xy is going to become what? Only thing we have that changes the horizontal stretch. 1/2 x. And my y stays the same. So mapping's way easier if you write the transformations first, right? If you write the transformations first, you know what's changed. You apply it to what you need to apply it to, and you go. Because your mapping is just doing what you're saying you're going to do. Okay? Example 7. I need you guys to describe the transformations and give me mapping. So, stretches. Are there any stretches? Are there any numbers in front? What do we always have to ask ourselves before we do any of this, actually? Is there a what in front of the x? A 1. If there's not a 1 in front of the x, what do we have to do? Greatest common factor, right? to GCF it till there is a 1. Yeah? Not greatest common factor technically. We just need to get the whatever's in front of the x away. Okay. Does this one have a 1 in front of the x? Yes, we can do it. So what kind of stretch do we have? Vertical. Vertical stretch by a factor of 2 about the x. Do we have a horizontal stretch? Is there a number in front of the x? No. Is there a negative in front of this 2? No. Is there a negative in front of the x? No. So no reflections. Translations? Horizontal or vertical? Horizontal because it's with the x. Horizontal translation, and with the x, if it's a horizontal stretch, we flip. If it's a horizontal translation, we take the opposite, right? So it's +1. So where are we going? 1 left. Okay, mapping, we do what we say. And we said a few things. So we said there's a vertical stretch. What does that apply to? The y. And stretches and reflections we multiply. So we're going to get what y? 2y. And then x minus 1. And then if they gave us a point or a graph, we would just plug in every point, get a new graph, done, right? Very easy. Okay, B, we ask ourselves, is it in y equals? Yes, because if it's not in y equals, we get it into y equals. Is there a 1 in front of the x? Yes. So for B, we are in y equals, and we have 1 in front of the x, then we can state our stuff. If we're not in that form, we have to move it. So stretches, do we have any? Are there any numbers in front of the f or numbers in front of the x? Nope, no stretches. Reflections. Are there any negatives in front of the f or negatives in front of the x? Yes, there's a negative in front of the f. So we have a reflection in the what? It's with the y, so it's in the x-axis. Because think about it, if I'm reflecting, if I'm changing my y's to negative, if it's up here, it's down here. If it's down here, it's up here. What axis am I reflecting in? The x, right? Okay. Translations. Is it with the x? At B? Nope. So it's what kind of? Vertical translation, B, down. All right. So we have x, y. Is a reflection in the x. So we have a, is it a negative x or a negative y? It's a negative y. And then we go B down. So minus B. Did anything happen to our x? No, our x is just sitting here nicely by itself, minding its own business. So it just stays. There it is. C, what's our issue? There's a negative in front of the x. Now, if it was like this, would I have an issue? No, but it's not like that, so I still have an issue. So I have to take that negative out. So I'm going to get y equals f. Take the negative 1 out, I'm left with x minus 3, which makes a big difference because I'm going 3 to the right, not 3 to the left. Will they have 3 to the left answer on your diploma and on my unit test? Absolutely. It's going to be picked most. So, but not by you guys because you're geniuses. You'll never fall for that, ever. Okay. The only issues are in the brackets with the x, correct? So there's going to be no vertical anythings. So we know in our mapping our y is going to be same. So if they gave us a point and it was like 2, 5, I would go to all my multiple choice instantly, and I would just cross out anything where the y wasn't 5. At least I'd have narrowed down, right? Okay. Stretch. Any stretches? Is there any numbers in front of the f or in front of here? No. Can my stretches ever be negative? No. What does the negative do? Makes it reflect. Okay. So we have a negative 1 here. So it's a reflection in the what? It's with the x, so it's a reflection in the y because we're making our x's negative. So if our x is positive, it's going to be negative. If our x is negative, it's going to be positive. And what axis am I dropping on? The y. Translations. Horizontal translation, 3, right. So x, y will become something and y. What's that something going to be? Close? Negative x plus 3. Okay, not too bad. Do example 10. How does the graph of 3y? What do I need to do here? First, 3 on the other side. So to move the 3 over to the other side, what am I going to do? Divide by 3. So I would technically have f of x over 3, which looks ridiculous. How else could I write it so it's not ridiculous? 1/3. Is it with the x? No. So what kind of stretch is it? Stretch by a factor of 1/3 about the. Okay, we have some replacement notation. What happens to the graph of the function y equals f of x as you make these changes? So you replace the x with 4x. You take the x, you rip it off your paper, and you input 4x. So we have y equals f of 4x. Yeah, what kind of stretch? Horizontal. By a factor of 1/4 about the. Now we're replacing the y, so we're taking this y here, we're ripping it off our paper, we're throwing it behind our head, and we're replacing it with a third y. So we get 1/3 y equals f of x. So we're going to get y equals 3 f of x. What kind of stretch? Vertical. By a factor of about the. He says with so much emotion. Okay. So I want you guys, example 11, using mapping, I want you to redraw this. Go. What transformations is this? What kind of stretch? Horizontal stretch by a factor of? Oh, so not true. Not negative. Can't have negative. Can't be 2. 1/2. Boom. Horizontal stretch is always flipped. The answer to it not flipping will be there, and you'll be wrong. So don't do that. Reflection in the y-axis. That's why there's a negative, right? All of it's affecting the x, so what's going to happen to all my y's? Staying the same. So xy becomes negative 1/2 x, comma, y. So if we took our points, we'd have negative 6, 0, negative 1/2 times 6 and 0 is negative 3, 0. So the y's are staying the same and the x are being halved. This is x of 0. So this point is what? Starts with an I, rhymes with invariant. Yes, invariant. What's here? I should have connected them as I was going along. Yeah, that's what it's going to be. No, it's not. Oh, that's sad. That's really sad. It's not reflected in the y at all. It's just been stretched. I didn't do negative. You see? I was like, if you look here, you can tell that this was going into my head. That it's reflected in the y. And then I was like, no, it's not. Boo. Okay, so instead of it being 3, negative 3 and 0, it's going to be 3 and 0 because you need to reflect it and squish it. This one's going to be 2, negative 2 and 0, so negative 2 and 2. So 2 and 2. That bad boy stays the same. This one is going to be 4 and 4, so now it's going to be negative 2 and 4 here. Negative 2.5. And then now does it look squished and reflected? Yes, before it was just squished. No reflected. It's just a sad wrong graph. That's what it was. Okay. So you're going to do example 12. And then we're going to move on to these ones, which I didn't make you do yesterday, where you have to come up with the equation from the graph. It's probably the hardest part. So we're going to do 12, and then we're moving on to, I give you all of them, what do you do with them? Okay. A. Horizontal stretch about the y-axis by a factor of 3/4. Horizontal stretch. Words getting put back in. What are we going to do? Yes. And it needs to be with the x. So if I go like this, is that with the x? No. How can you say it's with the x? What do you have to do? Okay. B. Y equals square root x minus 3 after a horizontal stretch by a factor of 4. Where does that go? 1/4. Where does that go? With the x. And this square root symbol is like a bracket, right? It's a square root symbol, but I just mean anything underneath the square root symbol is with the x. So we're going to have y equals 1/4 x minus 3. Out back. Then we have a vertical stretch by a factor of 2. If I give this question on the test, it scares me when I give it to you because people get it wrong. Vertical stretch by a factor of 2. Where does the 2 go? Outside, but what do we have to remember to do with it? Yes. So the 2 goes outside. People give me this answer and they're wrong. It will be there. It's wrong. You have to remember to apply it to the whole thing. So you get y equals 2 root 1/4 x minus 6. You have to remember that because the answer to the first version will be there. It's not right. Double what? What? Okay. The other answers on it would be making it be 4x if you forget to flip it, right? So your 4 options, I can make 4 options to this question really, really easily. You'd have this option without the brackets. You have this option, which is correct. You'd have this option without the brackets with a 4 here, and you'd have this option with a 4 here. So every single oopsie exists, right? That's why I said if you are like, I think I do that, that's bad. That's bad. We don't want to think, we know. Okay? Y equals 3x plus 7 after vertical stretch by a factor, about the x-axis by a factor of 1/3. So we're going to get y equals 1/3. And we have to remember to distribute it. We're going to get y equals x plus 7/3. Very important. If you don't remember to distribute it, bad news bears. Okay. And really, it only matters if you have a vertical translation, right? If you don't have vertical translation, there's nothing to distribute to. So then it's not a big deal. Okay, we're going to look at B for now. Okay. The function represented by the thick line is a stretch of the function represented by the thin line. Now this one is nice because it's just telling us all there is stretches. However, we're going to be given graphs where it could be anything. Reflection stretches. In this case, there's reflections too. So what we have to do is we have to do it in order, SRT, right? Stretches, reflections, translations, and the reason why I said that is because of bed mass. Remember, you have to do multiplication first, then addition, subtraction. Okay, so we have, let's compare parts of the graph that are similar. So this function represented, the function represented by the thick line is the stretch. So that's the new one, right? The thin line's the original. So let's look at this. It's obvious that this is flipped. Flipped where? On what axis? The x-axis, right? It's down like this. Now if I flip it back up, would it be the correct direction? No, it's also flipped in the y-axis. So I'd have to flip it this way and then flip it this way to get it to be in that same direction, correct? So we have reflections in both axes. I'm just writing that for our own welfare. Okay? And we also have to do stretches too, because both of those are multiplication ones, correct? So we have to deal with that first. So I'm going to compare things that are similar. So I'm going to go from the hook to this top part. How much is it? 1, 2, 3. I'm going to compare the hook to this top part. And it's 1, 2, 3. Did it horizontally stretch at all? No. Could you go from the hook till the end and the hook till the end? Whatever you want. You just have to compare the same pieces. Okay? So horizontally, this hasn't stretched. Vertically, I'm going to guess it's stretched, just because it looks like it did. But we will check it out. Okay, so I'm going to go from bottom to top. 1, 2, 3, 4, 5. I'm hoping this is 10. Why? Because if not, it's an awful fraction. So I'm going to hope it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And by hoping it's 10, I knew it was 10 because I made the question. So yes, it's 10. Woohoo! So we're going from 5 to 10. What are we doing? Multiplying by 2. So we know we have a vertical stretch by a factor of 2. To figure out our horizontal and vertical translations, it's not as easy. It is if, however, you take your original, stretch and reflect it, and then it looks exactly the same as the other one, and the only thing you're missing is the translations. Okay? So in order to find if there's any horizontal and vertical translations, what we're going to do is we're going to take the original, we're going to apply these lovely things to it, and then we're going to see if it's moved. Okay? So what are we doing to this original right now? Well, we're multiplying the x's by -1, and we're multiplying the y's by -2y. Okay? We're going to reproduce the graph and hope to goodness it's actually on the black one. If it is, yay, we're done. If it's not, it moved horizontally or vertically. Okay? Let's see. So we have a point. It is at 1, 2, 3, -3 and 1. What's it now going to be at? And -2. 1, 2, 3. Oh, this is looking better. This is a little bit. We'll pretend that that's actually there. This graph kind of stinks on my graph. Yay. Okay. Boom. This is looking good. This is looking promising. All right. Let's try another one. 1, 2, 3, and 0 and 3. It's not 3 and 3. It's 0 and 3. I don't know. I said 3 first. The catch here as well is on the diploma, they're not going to give you as shady of a graph as I just gave you because it's kind of a little bit off. They'll bold the points that are exactly on the cross sections so you know that it's specifically there. If it's not specifically on a cross section, they'll actually label the point and tell you what it is. Okay? They're way nicer than this not great version. Okay? So we're going to do 0 and 3. We're going to plug it into here. So we get -0 and -2 times 3. Which is 0 and -6. Boom. Oh my goodness. It's the same graph. Boom shakalaka. Has it been horizontally or vertically translated at all? No. So we can just apply what we did. We have y equals -2f -x. And I have my new equation. If it was off a bit, we would just figure out what the heck we had to move it to make it on. Right? So that's why you apply your stretches and reflections first. And then you can move it all you need to, up or down, to get it to land on it. It just happens to land on it already. Okay? Summary of what you learned. Hurrah! Okay. Example 1. Describe how the graphs of each of the following can be obtained from the graph of y equals f of x. First thing we need to do, get them in y equals. Second thing we need to do, make sure there's a 1 in front of the x. If that is the case, we can state everything, right? If that is not the case, we need to make it the case, okay? It's in y equals. We have a 1 in front of the x. Yay! All right. So what are our stretches? Do we have any? What kind of stretch? Vertical stretch by a factor of 1/2 about the what else do we have? Reflections? Nada. Translations? Yeah. What? What kind? Vertical. We're going to look at C, because I don't feel like walking over to B. You're welcome. All right. C, what's my issue? There's an issue. Gotta take that bad boy out. Yeah, that -2. She's an issue. Or he. It. Okay. So we take the -2 out, and we're left with x what? It's in y equals. We have 1 in front of our x. We can state stuff. Okay. Stretch. What kind? By a factor of? About the? So monotone. About the x-axis. Yeah. Is there a horizontal? Yep. Horizontal stretch by a factor of 1/2, because it flips every single time, not just sometimes. Like this is 100% of the time. So much so, 110. It's even more so. It will always do it. You will always flip it. 1/2. No, I said 100. About the y-axis. Perfect. Reflections, any? You got any negatives in front of those bad boys? Yep. Right there. What kind of reflection is it? In the y, because it's with the reflection in the y-axis, because we're taking the x's and we're making them negative. If we make x's negative, we're reflecting on the y-axis. Any translations? What? Horizontal translation 5, right. Now, instead of doing example 2 right now, I'm going to change it a tiny bit. I know you're excited, right? Okay. Y equals to f negative a quarter x plus 3 minus 1. Yes, fractions. You all like them. Enjoy. Okay. It's not a disaster. It's just fine. Okay. This is a disaster on the test, though, sometimes. So I will give it to you. It could be. But you're not going to make it a disaster. You're going to remember this. So when we took the -2 out of the last one, we actually did 10 divided by -2. Agreed? We're dividing to take that GCF out. We agree? Okay. Keep that in mind. So we have an issue with this -1/4. Pretend we don't have that one. We're going to go F. We're going to take a -1/4 out. You told me up here that you went 10 divided by -2 and it got you -5. We agree? Keep that in mind as you do this. 3 divided by -1/4 is -12. When you divide by a fraction, what are you actually doing? Multiplying by the reciprocal. Okay? Most people will get this one, but if I do this, had I done it this way, y equals f -1/4 x minus 12, a whole bunch of people tell me +3. Because this can go evenly into that. This one people will catch because I made it so the number doesn't go nicely into it. This one people will tell me +3. And if you're like, why is that not +3? It's because you're doing -12 divided by -1/4. which what do? You flip and multiply. So negative 4 over 1. So it would actually be 48, not positive 3, right? Okay, that's for that example. This one's made up as well. Okay, so we have to describe the transformations, and we're going to move that point. Describe the transformations, and then do mapping if we're moving a point. So we have, that's supposed to be an S. I don't know where I was going with that. S, vertical stretch by a factor of what? 2 about the horizontal stretch by a factor of 4 about the, any reflections? What? Reflection in the y-axis. Any translations? What kind of translation? Oh, good one. I forgot about that. Horizontal translation, 12, right? And if you just put 12 right and 1 down, you're not getting it. You're not. All right. Keep that in mind, Mr. I don't want to ever say any of those things because you need to. It's not just 12 right. It's a horizontal translation, 12 right. He scoffs. Hi, Mark. Okay. So x, y, anything with the x affects the x. So I'm going to multiply the x's by negative 4 and add 12. Oh, no, I need to close that. And what am I going to do to my y's? Multiply by 2 and minus 1. What is my original point? My original point is m and 3n. So for every x, I'm going to put in m. For every y, I'm going to put in 3n. So I get negative 4m plus 12 and 2 times 3n minus 1. So I get negative 4m plus 12 and 6n minus 1 is going to be my answer. Remember, transformations in grade 12 is harder than transformations in grade 11, first off, because transformations in the grade 11 doesn't have horizontal stretches or reflections in the y, but also it's only on quadratics, and you can plug them into your calculator. Can you plug this one into your calculator at any point in time? No. Twofold, it has an F in it, so you can't. And second off, the point is m and 3n. What is that? I don't know. Okay, so twofold why you cannot plug this into your calculator. So